My name is Takahashi. I will talk about a classical algorithm for simulating quantum circuits with local depolarizing noise. This is joint work with Yuki Takeuchi and Seiichiro Tani. This is the abstract of my talk. We study the effect of noise on quantum circuits that are hard to simulate classically in the noise-free setting. Here, we consider a noise model where a depolarizing channel with an arbitrarily small constant rate, epsilon, is applied to each qubit at the end of computation. Our main result is that under this noise model, if an approximate value of epsilon is known, such circuits are classically simulatable. This indicates that the presence of small noise drastically affects the classical simulatability of such circuits. The background of our study is as follows. A key step toward realizing a universal quantum computer is to perform computational tasks that are classically hard. As such a task, many researchers have focused on simulating quantum circuits, or more concretely, sampling their output probability distributions. This task is known to be classically hard for various quantum circuits that seem easy to implement, such as IQP and Clifford magic circuits. I will describe these circuits later. Our question is whether this task is really classically hard. This is because the classical hardness results have been obtained in severely restricted settings, such as noise-free setting. So there is great interest in considering this task in a more reasonable setting. Here we consider a noise setting. First, we consider a quantum circuit in the noise-free setting. A quantum circuit is a sequence of 1 and 2 qubit quantum gates. The number of gates in the circuit is polynomial in the input length n. We prepare n input qubits initialized to 0. We apply a quantum circuit C to the input state. After that, we perform measurements on the resulting state. We obtain the classical outcome of the measurements, which is an n-bit string. The probability of obtaining X is computed like this. This defines the output probability distribution of C over n-bit strings. It is known that under plausible complexity theoretic assumptions, the output probability distributions of various quantum circuits are not classically samplable efficiently. We give examples of quantum circuits that seem easy to implement and whose output probability distributions are not classically samplable efficiently. This is an instantaneous quantum polynomial time circuit, which consists of Z-diagonal gates sandwiched by 2 Hadamard layers. This is a Clifford magic circuit. The first 2 layers generate magic states, and then Clifford circuit is applied. This is a conjugated Clifford circuit, that is, a Clifford circuit conjugated by an identical 1 qubit gate on each qubit. Each type of quantum circuit has an output probability distribution P over n-bit strings, such that P is not classically sampleable in polynomial time with certain constant accuracy in L1 node. Moreover, P is anti-concentrated. That is, the sum of the square of the probability of obtaining X is upper bounded by some constant divided by 2 to the power of n. Motivated by these examples, we consider a new circuit class which we call CT-ECS. This class consists of a quantum circuit C represented as BU like this that satisfy the following conditions defined by two concepts, CT states and ECS operations. The first condition is that U0n is computationally tractable. Roughly speaking, this means that it is possible to classically compute this value and to classically sample the probability distribution defined like this efficiently. The second condition is that V dagger ZJV is efficiently computable sparse, which means that this state is a superposition of at most polynomially many computational basis states, and it is possible to classically obtain this representation efficiently. I do not give further details here, but an important point is that all the quantum circuits described before are CT-ECS. For example, any IQP circuit is CT-ECS. This is because if we regard this part as U and this part V, we can show that U0n is computationally tractable and V dagger ZJV is efficiently computable sparse. Similarly, we can show that any Clifford magic circuit is CT-ECS by regarding this part as U and this part V. Moreover, any conjugated Clifford circuit is CT-ECS by regarding this part as U and this part V. This means that various CT-ECS circuits yield probability distributions that are not classically sampleable efficiently and are anti-concentrated. We consider CT-ECS circuits in a noise setting. The noise model is one where depolarizing channel d epsilon is applied to each qubit at the end of computation. Here, for any one qubit state low, the epsilon leaves the qubit unaffected with probability 1 minus epsilon and replaces its state with the completely mixed state with probability epsilon, where epsilon is an arbitrary constant between 0 and 1. We prepare n input qubits initialized to 0. We apply a CT-ECS circuit to the input state. Under this noise model, the epsilon is applied to each qubit at the end of computation. We perform measurements on the resulting state. This defines the output probability distribution P epsilon of C under the noise model. Let P be the output probability distribution of this circuit in the noise-free setting. It is known that P epsilon can be sampled by the following procedure. Sample an n-bit string according to P, and then flip each bit of the string with probability epsilon divided by 2. Our question is whether P epsilon is classically samplable efficiently. This is our result. We consider a CT-ECS circuit under the noise model. We assume that approximate value of the noise rate epsilon is known, and assume that the output probability distribution of the circuit in the noise-free setting, which is P, is anti-concentrated. Then P epsilon is classically samplable efficiently. This is an extension of the result by Bremner et al. In 2017. They showed that this relation holds when the exact value of the noise rate epsilon is known and the circuit is IQP. As described before, in a noise-free setting, various CT-ECS circuits yield probability distributions P that are not classically samplable efficiently and are anti-concentrated. So when we apply our result to such a circuit, P epsilon is classically samplable efficiently, although P is not. Thus, our result indicates that the presence of small noise drastically affects the classical simulatability of CT-ECS circuits. This is a more precise description of our result. Let C be an arbitrary CT-ECS circuit on n qubits, where P is its output probability distribution and anti-concentrated. That is, this sum is upper bounded by some constant alpha divided by 2 to the power of n. Moreover, P epsilon is the output probability distribution under the noise model with possibly unknown constant rate epsilon. Let delta be an arbitrary constant, which is an approximation accuracy. Let lambda be an arbitrary constant, satisfying this relation, which is an approximate value of the noise rate epsilon. Then P epsilon is classically samplable in polynomial time with accuracy delta in L1 norm. More precisely, there exists a polynomial time randomized algorithm that outputs a classical description of a probability distribution Q such that it is an approximation of P epsilon with accuracy delta in L1 norm with high probability, and it is classically samplable in polynomial time. To prove this theorem, we generalized the previous proof for IQP circuits. The probability distribution P epsilon, which we want to approximate, can be represented like this, where P hat of S is the Fourier coefficient of P, and this is the relation between P and P hat. To approximate P epsilon, we first approximate the Fourier coefficient P hat of S for the circuit C with S, whose Hamming weight is less than or equal to C, where C is a constant depending on alpha associated with the anti-concentration assumption, the approximation accuracy delta, and approximate value lambda of epsilon. By choosing C appropriately, we can show that P epsilon is close to the function Q prime, defined like this, where P hat prime of S is an approximate value of P hat of S. Then we sample a probability distribution close to Q prime. An important point is that this circuit is an arbitrary CT-ECS circuit. In the next slide, we give an idea of how to classically approximate P hat of S for a CT-ECS circuit. To approximate P hat of S, we show a new relation between a quantum circuit C, which is VU, and P hat of S. P hat of S can be represented like this for any n-bit string S. As described in the previous slide, it suffices to consider only S whose Hamming weight is constant. This implies that this red part is efficiently computable sparse. This is because this operation can be easily transformed into this form, which is a product of a constant number of ECS operations. Thus, by this new relationship, 2 to the power of n times P hat of S is the value of this form, described by a CT state and an ECS operation. Thus, we can apply a polynomial time classical algorithm for approximating the value of this form, proposed by Nest in 2011. Thus, we obtain an approximate value of P hat of S for an arbitrary CT-ECS circuit efficiently. In summary, the presence of small nodes drastically affects the classical simulatability of CT-ECS circuits. This is obtained by our result that, under the noise model, any CT-ECS circuit with an anti-concentrated output probability distribution is classically simulatable. An interesting challenge would be to extend our result for a broader class of quantum circuits in a more reasonable setting. For example, it would be interesting to investigate whether we can analyze the effect of noise on Shor's factoring algorithm in a similar way. Thank you for your attention.